Now at the input, you guys have any questions?
Should for the bottom case, shouldn't they both be grounded?
Okay, I am trying to get a fan out for logic 1. So fan out for logic 1, which means logic 1 at the output of the first stage. It means the input of the next stage is at logic 1. So this is at logic 1, this is at logic 1. And for this case, this is being grounded by some other gate. This is at logic 1. You have a gate, right? 0, 1, 1, 0. You can have this combination as well. You can have this combination as well of inputs. You follow what I'm saying now? Please raise your hands if you guys are with me. Okay. You follow? Still? No. Okay. In a digital circuit, let me just generally explain it. You feed number of gates at the outputs, similar gate, right? So they have like number of inputs. Right now we're talking about 2 inputs. Now those 2 inputs have combinations like NAND gate 0, 0, 0, 1, 1, 0, 1, 1, right? Now when we're talking about logic high, you have 3 cases in which you have logic high. Number 1, where B is high, but A is sitting at 0. Number 2, A is high when B is sitting at 0. Number 3 cases when both are 1. These 2 are similar, right? One is on, one is off. So I'm saying you can have a case where you have n number of gates and you're feeding the inputs like this when one is grounded. What's my current in that case? When one is grounded and one is at logic 1. This is my previous gate. It's connected to this gate. You can have n number of gates. We don't know what that fan out is. We're going to find out, right? But you can also have a case where both of the inputs are at logic 1. In that case, what is my current that's going in? Okay. Now we are looking at a maximum value. You know why? Because if the current is high, you are pulling, you're drawing more current, right? This voltage is going down. If this voltage is going down, it can go below VIH. And what happens if it can go below VIH? You're in the forbidden range. Your gates will not be able to detect whether you have a logic 1 or logic 0 at the output. You follow it or no? Yes or no? No in the middle.
Yeah, I think
Okay. But let me just complete the problem. Maybe you'll understand it better. So I'm going to do case 1. Case 2 is easy. Now for case 1, right, I'm drawing the input transistor of the next stage. Okay. This is at logic high, say 5 volts, and this is at logic low. And what happens here? Yes.
So in this situation, because one of them is grounded, that means wouldn't most of the current flow through that grounded one?
Yes, yes, yes.
Basically,
It's gonna flow this way.
Yeah.
So it's gonna turn
that off.
that off. We have nothing here. I have a resistor here. I don't know what's the value of that resistor. That's 540. Thank you. Okay. Now you see in your given parameters there is one parameter named as beta L. That's 1. Right? Now this guy over here, nothing is here, right? So you have this configuration. Now these 2 emitters are embedded in this one transistor. Now one is sitting at a high volts, 5 volts, another one is grounded. Okay. So it itself acting as a lateral transistor. I'm going to redraw this. This is 4K and that's 5 volts. This is 5 volts. This is grounded. So this node is at higher potential than this one. So whatever node is at higher potential, the current in that branch will be related to IB through beta L as beta L IB1. Okay, and the current here, although we are not interested in this, beta L plus 1 IB1. Now what is this node here, which is at logic high? And what is this node here, which is at logic low? We are not talking about that, but I want you to know that. I want you to understand this. This is for worst case input high requirement. If it is worst case input low requirement, then you have to work with this current. You're going to have two cases. One is that one input is either low, one input is low, one input is high. And the second case is when both of the inputs are low. And then you have to do the comparison and see which current is maximum. Yes?
Is that because in this situation, VO is high, so it's being connected to the high output is being connected to the emitter on the other one.
Yes.
So it's a one being sent to that one.
Yes,
But
yes,
if
yes.
it asks
This is the
for-
next stage, this one.
Okay, so
Case one. So I said this is case one.
yeah. So in
Right
the
here.
opposite scenario, VO would be 0, so that's basically grounding it. So the current that's flowing from there would be the one that's connected to the.
Yeah, it is gonna flow into the circuit.
Okay.
Syncing.
Yeah.
This we are sourcing.
Okay.
Okay.
Okay, that makes sense.
Now we are interested in what? IIH, right? What is IIH now for this case?
Yeah, beta L.
Beta L,
I-
IB1. And what is IB1 here? What is beta L? 1. And what is IB1? This is grounded. This is 0.7 volts, right? This base is sitting at a higher voltage than this one. This is 0.7 volts, so that's 5 minus 0.7 volts divided by 4K, right? So that's 5 minus 0.7 divided by 4K. So what is that correct? I don't have the calculation here.
Like 1.1 billion. Yeah, 1.07.
I hear two different values.
I was rounding 1.07 million.
Case 2, I might have it. 1.075 milliamps, right? Perfect. Now this is one case is done, right? The other one is easier. How? Can I erase this? So I'm doing this case now. IIH case 2. So this is the next stage. This is logic high. This is logic high. These are on. Right? And case 2. 4K, 5 volts. Q1, Q2. Q3. Okay. If this is both are high, what's happening here? This guy is on, this guy is on, and this is off, right? Good. You guys follow what I did here? I'm just drawing the circuit of the next stage. Now it's very easy to get. What's the current in this one branch?
Beta L or IB1 divided by 2? Is it divided by 2?
No, it's not divided by 2.
Okay.
Because you have a same base current that's going in, right? The two emitters are embedded in this one transistor, they have the same base current. If I had a transistor like this, which I had drawn in the class, and here the base current is split.
So instead of the emitters being embedded in,
Yes, you
they're
embedded in
separate.
just one transistor.
Okay.
They have the same base current.
Okay. So it's just beta R IV1.
Yes. So here, your IIH in one input. That's beta R IV1.
Question.
What is beta R? That's 0.5. And what is IV1 here? This is on 0.7, 0.7, 0.7, because this is acting as an,
Oh wait. Yeah.
this is acting as an emitter, this is acting as an collector. You said that beta R IV1. You only get beta R IV1 if these two inputs are acting as an emitter, collector. Okay, so 0.7, 0.7, 0.7 times 3, 2.1 volts, right? Okay, let me just finish this, I'll answer your question. So that's 5 minus 2.1 divided by 4K. That's gonna give you 362.5 microamps. Wow. Case 2 is 362 microamps, and what do we have here? Which one is worse?
One high, one low.
So now you've got IIH, worst case requirement. What if you are asked to find the IIL worst case requirement, right? The first case is right here, right? You can find the current here, which is beta L plus 1 IV1. For the second case, what are you gonna have to consider?
Both zero.
Can I use this board? It's just the corner. A, B, B now. So I'm writing 0, 0, 0, 1, 1, 0, 1, 1. So that's 1, 0, 0, sorry. Okay. I'm just gonna omit this thing, right? Because 0, 1 and 1, 0 is the same thing. It's just gonna confuse you. Just give me 1 second. Let me just finish with this topic. 1. Okay. I'm talking about the worst case input requirement for the next stage. So you can have these 3 types of setups. Okay. For IIL, worst case, you have to do 2 cases. First is for when both A, B are 0, 0, IIL, right? Second case is when one is low, other one is high. So you want to find a current in this branch. For this one, you will be using the lateral transistor, and that current is beta L plus 1 times IV1. And for the first case, it's easy, right? Because both are low. So what's happening is we have 2 diodes. Whatever current that we have here, that's going to split into 2 branches. And you are interested in just one branch, right? You guys follow what I'm saying? So this is sitting at 0.7 volts. This is 5, whatever the resistance is. So for this case, your IIL would be 5 minus 0.7 divided by 4K times 1 over 2. This node, everything else is off here. So if I ground these 2, this is off, right? If this is off, the current is flowing this way. Think of this as 2 diodes, as I have shown here. So this base is sitting at 0.7 volts. So the base current is 5 minus 0.7 divided by 4K. It's splitting into 2 branches, but we are interested in looking at only one branch. Okay? So these are the 2 cases when you are asked to find noise margin for logic low. We are right now doing it for logic 1. Yes, questions?
Could you explain the relation of the IH one if one of those conductors becomes an emitter? I'm not sure if we just
Oh, for the lateral transistor? Yes. So what's happened is, easier to look at the physical diagram. So let's say this is your collector, this is your base, this is your emitter. And I'm talking about NPN transistor, just my top view. Now what we are doing is, we are saying, let's say we have 2 emitters in the base. And they are N-type. E1, E2, and they are N-type. Now one of them is at 5 volts, another one is grounded. You see, this is an NPN transistor, just a part of the transistor, the whole big transistor. If nothing is flowing here, this itself is acting as a NPN transistor. That's your lateral transistor. So whatever input is at high logic, that's your collector. And the other input which is at low logic, that is your emitter. Okay? And the gain associated with this transistor is represented as beta, which is 1. That's given. Okay?
Yeah, I just want to make sure. So the reason why we divide this by 2 is because the current in this situation is pulling current through both of the inputs, because they're both set to 0. So the voltage between the 2 inputs and the base is like, so the current flows this way, but then divides through both of the
Yes,
inputs evenly because they're both basically the same.
exactly. It's the same inputs, diodes.
Okay, but the opposite direction, there's no situation where the current is flowing through both at the same time, so it wouldn't split into 2 in that scenario? Like, in this situation, we have the current flowing through because they're both 0, we have it flowing through both inputs. When we're working
You
with the
understand that?
Yeah,
Okay. Both are at high. So you're saying this current should be half of beta RIP1. That's what you're saying?
No, I'm saying because they're both high, basically all the current's gonna flow down, because
Oh,
they're-
yes,
Yeah.
into the transistor.
Yeah,
Yes,
so
it's
basically the current's
sourcing
not
the
being,
current.
yeah, it's
Yes.
not being divided up at all, it's literally just going one current from the collector, and we're
Yes,
only worried
it's
about
one current that's going to the emitter.
Okay.
So here, your current is basically, which is an emitter current,
Yeah.
that is a sum of IB plus what's the current here? Beta RIB, and what's the current here? Beta RIB. So that's going to be IB plus beta RIB plus beta RIB, and that's going to be 2 beta R plus 1 times IB. It's going into the circuit.
Okay.
So both are high, the current is going into the circuit.
Okay.
Both are low, the current is going out of the circuit.
Okay.
That's what you're asking, syncing, sourcing?
Yeah,
Just
no.
trying to understand.
No,
I
I'm
don't
just
think
trying
I
to
follow
like
your
make
question.
sure that like the reason why we're dividing it in this situation is because the current is flowing through both of the inputs and not. in
Yes,
other
because
situations.
everything else is off to the next of the transistor, right?
Yeah.
So if you set both of these low, like for example here, set both of these low, all of the current is gonna flow here, right? All of the current is gonna flow here, this is off. So if both are on, both junctions are on, right now it's at Y, if both are on, this current is gonna get divided into 2 branches. Because they're acting as a diode, base emitter diode. Okay?
So in this situation where we have 2 highs, does that mean, right in that section, does that mean that the current through the emitter there, or where it's acting as an emitter, does that mean that it's equal to 2BR plus 1 times IB?
Yes. 2 BR beta R plus 1 times IB. That's what's going in, turning this transistor on.
Okay.
Okay? Alright, what is the time? Alright, this was worst case IH requirement. Let's just do the I not available. Can I erase this? But do you understand the concept of like worst case now? I hope you guys do. Yes? Alright, I not available. For logic high. Okay. Logic high means this is off, right? So redrawing the circuit, you're gonna get 1600 Q4 diode, this is V naught, 100 ohms, 5 volts, 5 volts. That's IB4, IC4, IP4. And is V naught any noise margin given in the problem? I think there was. What was the noise margin? 150 millivolts?
Yeah.
And then your VOH will become VIH plus 150 millivolts. That's going to give you .75 volts. You guys understand this circuit? Okay. So what is I not available here? IE4, right? So I not available is simply IE4, and that is equal to IB4 plus IC4. So our job is to find IB4 and IC4. What's the drop across this diode? This is on, that's 0.7. What's the drop across the base emitter junction of Q4? 0.7 volts. And can we find the voltage here at this node? KVL. This voltage equal to this plus this plus this, right? So the voltage at VB4 is 0.7 plus 0.7 plus 1.75 volts. What's the value here? Say it again.
3.15 volts.
3.15
0.15.
volts. Now, can we get IB4?
Yes.
Okay, IB4 is 5 minus 3.15 divided by 1600. Whatever that correct is. Now, IC4,
Beta 4. Is it beta 4 to IB1?
this transistor is in the saturation region. What's the drop across 0.2 volts? So that's going to be, IC4 is going to be 5 minus 0.2 minus 0.7 minus 1.75 divided by 100 ohms. Good. Now just add these two values. I believe my calculations are correct. That's going to be 24.66 milliamps. Good. Now you have I not available. You have worst case input high requirement. So your fan out for logic high would be, what was the value here? 24.66 divided by 1.075, right? That's gonna be 22.93, and we always take the low value, that's 22. Now you should be able to solve it for logic low at the output. Good? Alright, let's do next problem. Next is simple. The major part of the interview session is done. So now it's just BJT inverters and diodes. But I hope you guys understand the concept of fan out now for worst case situation. Alright, let's do BJT inverters. Can I erase this? Oh.
Yeah, how do you return this one? Like you're trying to say how do you
So, how, do you want to ask me my Chinese name?
Yeah, just what you're trying to say.
My Chinese name? I didn't look at that yet.
How do you? Is that moon? Is that moon?
No, it's, yeah,
Okay, I'm gonna leave the first two parts to you guys. That's easy. I'm sure you guys can figure that out for your own. And I'm gonna upload this these review problems on Sakai as well later tonight.
Chow Chang too.
This is given. The first part of the problem is we have to find VOL, VIL, and VOH. Okay. No output load. In the second point, you have to find VIH. Okay. I'm gonna leave this to you guys. I'm sure you guys can do this. Yes or no?
Speed run.
The second part.
Speed run.
I have a meeting after this, so I'm gonna run real quick. So what is VIH? Definition wise.
It's the lowest
Minimum value.
registered one.
It's the minimum input voltage to be measured as a high, as a
Okay.
logic one.
So minimum input voltage. So if I look at this transistor, right? That's logic high means this is on, right? So what's the voltage across Q1? That's 0.7. And it will be some current IB times 20K. Okay? So we are looking for a minimum voltage which is enough just to saturate this transistor. So what is this IB then? Can someone tell me please?
IC sine of beta.
forward?
I'd be like edge of saturation.
I'd be edge of saturation.
Edge of saturation, yes, that's correct. So that is simply
IC set.
IC sat divided by beta F times 20K plus 0.7 volts. Now you get problems, right? IC sat is what? 5 minus 0.2 divided by 1. Okay. And what about this VOL? 0.2, VIL? What is VIL? What's the definition of VIL?
Voltage input low.
Maximum input voltage, for logic 0.
Yes. So what's that voltage? Logic 0 means the transistor is off. Transistor off, there is no base current. Then what is VIL?
0.
VIL is the maximum voltage. Yes. Very good. What's the voltage across this transistor that we need to turn this? I mean, the maximum voltage that we can afford to keep this transistor off. That's 0.5 volts. This is off, no current flowing here, so VIL is 0.5 volts.
So that 0.5 volts, is that an assumption that we're making, or are we getting that from subtraction that I'm not remembering? Or-
We're not making an assumption. VB cut in is 0.5 volts.
Okay.
So that is, you
Okay.
should know that by now.
Yeah, I wasn't
I'll
sure.
just provide that if I give you this problem.
I wasn't-
Yeah, one thing I want you to understand is, I'm giving you a review session in a way so that you will be able to do the exam problems. But you won't see the exact problem in the exam. Just wanna be very honest about that. Okay,
So format wise, we're gonna have like multiple choice or just open ended?
no multiple choice.
And
It's
how
gonna be
many
like
questions
this.
are we expected to get?
It's gonna be like this, the way I'm doing it.
So like
First
three-
problem, second problem, this is the third one, and then I'm gonna do the fourth one after this.
Okay.
Okay?
So it's 4 problems.
4 problems.
On the exam.
That's why I don't like giving the review session. I can't just keep the information to myself. You know what I'm gonna do? If I give a review session, I'll try to give it like a week and a half. Or
What's the
after that, I'll make the exam.
What's the point of the- what's the point of
Alright,
the
anyways,
research?
let's get to the next problem. Next section. So the third part of this problem is you have to find TF. Okay, for this inverter. I have to look at the time.
It's 25.
6.4.
Okay, so we have to find TF for the inverter for when you have 100 picofarad load capacitance. Okay, so you have to calculate the fault time. Do you remember the waveform? Comes when input goes high, right? Input goes from 0 to 5 volts. I should have provided that. Okay. So this is your input going from 0 to 5 volts. When your input is 0 to 5 volts, what do you think the output, how the output should look like? So you have a delay current. If I plot the base emitter voltage, right, of the Q1, it's gonna look something like that, right? Okay. And what is this T2 minus T1 here?
Rise time.
Huh?
TD.
Delay time. What did you say?
Rise time.
Don't scare me. Alright. So the output high, right? Since the output is what? Yeah, it's high because the input is low. At T2 it's gonna drop to 90% of VOH, right? If this is your VOH, it's gonna drop to 90% of VOH. And then after your diode is on the base emitter junction, right? gonna quickly, or you can say the capacitor at the output is quickly discharged. So your output is gonna fall to 10% VOH. So what is this time? Fall time. This is what we are interested in. I'm going to call this T1, T2, T3. Okay. Now if you remember that one formula, right? I think I provided this in the formula sheet as well. I think I did. This is CV dot, right? And I can write this as QCB. So delta T would be C delta V over I, right? Yes.
So when we have that load capacitance, does it take over the role of the depletion capacitance? Or the diffusion capacitance, the CJ?
Okay. So the way we had done this analysis for fall time and rise time, for this specific particular interval, we had mentioned that the load capacitance is much higher than the device capacitances.
Yeah.
So we're not going to take into account the effect of all the device capacitances.
Yeah, so this one like takes over basically, right?
Yeah.
Okay.
Okay. What I'm going to do, I'm going to draw the model and maybe write down the equations. Okay. So for the fall time, if you look at the base emitter voltage, that's positive 0.7. What about the base collector voltage? This is base, which is 0.7. In this specific interval, the collector voltage is decreasing, right? So the base collector voltage here most of the time is reverse biased. Base emitter is forward, base collector is reverse biased. So we can model the transistor for this case as a current source, right? So I'm going to replace this transistor as a current source. And I have a load capacitance here, CL. This is my I0 and this is my IC, 1. Okay, and right here I have 1 k ohm resistor. Good. Now the voltage here, the output voltage, right? So this, if you look at this formula, this is delta V naught and this is I naught. That's what's changing the voltage in the load capacitance, right? The voltage change and the current change. Now this current, voltage change is easy. What's the voltage change? That's 90% of VOH minus 10% of VOH, right? That's what, 4.5 minus 0.5, that's going to give you 4 volts. You see what I did? Your VOH